group of K, which is being everybody has defined the class group, but still once again I just repeat, the class group is actually a factor group of sort of all a group of fractional ideals factor principal fractional ideals of K. So in this, it is well known that the class group is finite abelian group. If and I denote H of K is a Hilbert class field of K, which is a maximal unramified abelian extension of K. And I define something called conductor of abelian number fields, which is defined to be smallest natural number n such that K is contained in Q zeta n. We know that any abelian extension is contained in some Q zeta n. Such a smallest one is called a conductor. So actually, Euclidean ideal is some generalization of Euclidean domain, but just see the definition of Euclidean domain before. An Euclidean domain R is a integral domain R is said to be Euclidean domain if there exists a function phi from R to n union 0, such that for every alpha, non-zero beta, there exists a y belongs to. Okay, this is not this is the ring R, not a real number R, such that phi of alpha minus beta y is less than or equal to phi of beta. So now we see that actually that Lenstra has introduced the Euclidean ideals in 1979, which is a generalization of Euclidean domain, and also it actually captures the class group. We'll see how it captures it later, but so the definition of Euclidean ideal is this, and we can actually see there's some kind of similarity. Actually, I do not have time to explain everything, but otherwise there is a nice. You can also see that if you have a Euclidean domain, which is, if you have a principal ideal which is Euclidean ideal, then we can actually show that it actually going to be Euclidean domain. That is simple calculations we'll have to do. So the Euclidean ideal is defined. Let's define the Euclidean ideal. Let R be Euclidean Dirichlet domain and I be the set of all non-zero or integral ideals of R. If C is an ideal of R, is said to be Euclidean ideal if there exists a function psi from set of all ideals to n such that for every I belongs to I, X belongs to I inverse of C minus C, there exists a Y belongs to C such that psi of X minus Y into IC inverse is less than or equal to psi of Y. You can see there is some similarity between Euclidean domain and the definition of Euclidean domain Euclidean ideal. Actually, Euclidean ideal you can even define it for a general integral domain as well. But Lenstra is even actually defined for general Euclidean integral domain. But later on, he went on to prove that if there exists a Euclidean domain, that integral domain has to be Dirichlet domain. So I've started with R to be Dirichlet domain. Okay. So the consequence of existence of Euclidean ideal, if C is a Euclidean ideal, then every ideal that belongs to the ideal class of C has to be Euclidean ideal. Then ideal class C is actually, if C is a Euclidean ideal, then the ideal class C is called Euclidean ideal class. Then how is that class group and Euclidean ideal class is related? So if C is a Euclidean ideal of K, then the ideal class C generates the class group of K, which means the class group is cyclic. So actually the existence of Euclidean ideal implies that the class group of K number field is cyclic. So this is something I actually spoke already, but if a principal ideal is Euclidean, then OK is an Euclidean ring. And if suppose OK is Euclidean domain, then any principal ideal is a Euclidean ideal. So now question is, does CK, I mean the class group cyclic implies the existence of Euclidean ideal? Not necessarily. Does it implies the existence of Euclidean ideal? Like for example, imaginary quadratic fields, we know that these are actually Euclidean ideals, Euclidean domains, but they are not PIDs. Sorry, they are PIDs but not Euclidean domains, which means they don't have a Euclidean ideal. Sorry. So under the assumption of GRX, the Lenstra actually proved that whenever the OK star is greater than or equal to 1, the class group is cyclic if and only if K has a Euclidean ideal. So this is all the works that are done towards the Euclidean ideal are just to remove this assumption of GRH. That's all. Most of the works have been. I'm sorry for. So one such is, so actually the Ramurthy and Graves I've actually proved a certain class of number fields, abelian number fields, where the unit rank is greater than or equal to 4. They actually proved that it has an Euclidean ideal without the assumption of GRH. So if K is a number field, which is Galois over Q, and if H of K over Q is Galois, then and also the rank of OK star is greater than or equal to 4, then class group is cyclic if and only if it has a Euclidean ideal class. And the same result was being generalized by Shauli Gun and Josna Shivaraman and Dishulas. So what they proved is, if K is a number field with a rank OK star at least 3, which is greater than or equal to 3, and with almost same assumptions, but they have one extra assumption that the Q zeta F over K is actually cyclic. So this is actually quite a, it is I felt it is something more to ask. It's very rarely, not very rarely, but most of the cases they don't satisfy this property. But that is why, for example, if I consider biquadratic field, this one, so this Galois group is actually isomorphic to this, which is not cyclic, where this F is actually this, which is the conductor of Hilbert class field of K, and here the rank of OK star is 3. Actually, I consider to be a real biquadratic field. So actually, we looked at actually this particular one has the class number equal to 2. So we have even looked at class number being prime. So K be the real quadratic extension with the prime class number, and the Hilbert class field is abelian over Q. Almost same assumptions, but let F is equal to LCM of the conductor of K and 16. You will see why this is F to be. We should consider this. And if G is a Galois group of Q zeta F over K, and GAB Galois group of Q zeta F over Q zeta L, GLB, and G is not contained in this. So it is not, G is not completely contained in union of GLs and gal of Q zeta F over H of K, where L is any odd prime dividing F, or L is equal to 4. Then we have then we can say that K is a Euclidean ideal. Okay. So before proving this, we got a nice result. We applied this to a biquadratic field and we got a nice result. And let's see what is that. So actually, if you see the Euclidean ideals in biquadratic fields, when Graves proved the theorem about OK star, when he proved existence of Euclidean ideal in OK star, the rank of OK star being greater than or equal to 4, then itself he has constructed a biquadratic field Q zeta 2 Q adjoint root 2 comma root 35, which has a non-principal Euclidean ideal class. So this was generalized by Hasu, and he has proved that whenever whenever K is equal to Q root Q comma root of KR has a non-principal Euclidean ideal class whenever this has a class number 2, and with some other conditions that all the primes that he has considered here has to be greater than or equal to 29. And this was much more generalized by Jaitra Chattopadhyay and Subramani Muthukrishnan. They actually proved that Hasu assumed that all QKR are congruent to 1 mod 4, but Jaitra and Subramani has they wanted only Q, means both K and R to be congruent to 1 mod 4, and Q can be congruent to 3 mod 4 as well. And I actually proved recently that even Q can be even one of the K or R can be congruent to 3 mod 4. Okay. So actually, if I apply the main result that I have stated, if I apply that, I get that if K is equal to Q adjoint root Q comma root RS, real quadratic field with the class number 2, if P, Q, R all distinct odd primes, that's all I need. I don't need any other conditions. Then I can actually prove that this has a Euclidean ideal. Okay, so actually all these results have used something called growth lemma, where you have something like, without assumption of GRH. Here, Graves have proved that whenever K is a number field with OK star is infinity, which means it has rank at least 1, or else it has rank at least 1, then C is a non-zero ideal of OK, and also it generates class group, and also you have such this set, the set of all primes, such that they lie in the ideal class as same as C. If this count is greater than or equal to x by log x square, then this has a Euclidean ideal. That is what Graves have proved. And actually, I've actually found a sequential version of this, which was proved by Gun and Josna Sivaraman. So what they have proved is the same assumptions they kept, and they say it is not necessarily that it should happen for every x, but it is enough to say happen for unbounded increasing sequence xn. So if you have something like this for an unbounded increasing sequence, then we can actually say that the ideal C is actually Euclidean ideal class. Okay, so this is one of the important that I'm going to use for the proof. So what it says is suppose whenever U and V are the natural numbers with the following properties, which is the GCD is 1 and V is congruent to 0 mod 16, and U minus 1 by 2 comma V is 1, and there exists a B comma C belongs to 1 by 4 comma 1 by 2 with a P less than or equal to C, B less than C, such that any epsilon greater than or equal to 0, we have this set J epsilon. Okay, this is I'm counting some primes which are these are always going to be greater than or equal to x by log x square. Okay, primes less than or equal to x. Okay. And so they actually P is congruent to U mod V. That is something we will use. Okay, so let's get to the main proof. So just to show you once again the main theorem, I just here. So let's get to the theorem. So before that, let's see some lemma. If, with the same hypothesis as the main theorem, if I have, then I can say that there exists A belongs to Z such that for any prime P, such that P congruent to A mod F splits completely in K, but does not split completely in H of K. It splits completely in K, but not in H of K. Furthermore, there exists a B comma C belongs to 1 by 4 comma 1 by 2 such that for any x comma epsilon greater than or equal to 0, we have something like this. So here is where I'll be using Heath-Brown's lemma. But let's see, quickly go through how does the proof work. So I have this assumption in my main theorem. So suppose there exists one sigma sigma from here, which sigma from G but not here, then I can use this isomorphism between the cyclotomic field and the Galois group of cyclotomic field and this thing, and I produce a A, and this A will work, and the splitting in K, not splitting in H of K is completely we can get it by using the Artin symbol, which is easy, just some calculations, and then now applying Heath-Brown's lemma for U is equal to A and B is equal to F, we can actually get J epsilon of x is actually greater than or equal to x by log x square. Okay, so let's continue the proof. And actually, till now, the J epsilon of x that I consider, that was a completely, we are looking at a primes in over Q, right? But now I want to look at the primes in K. So what I do is I construct a set M epsilon, which is primes of OK, such that this now what should I say? This norm of P is actually it has degree 1. It's just a prime, and that prime should belongs to J epsilon of x for some x. That is all what it is written here. So then now let me consider M epsilon of x is actually P belongs to M epsilon. Okay, which such that N epsilon is less than or equal to x, and it is clear that this is less than or equal to this, which is greater than x by log x square. So here I again use a lemma by Gun and Josna. So what they actually proved is that whenever K be a totally real field and non-zero elements, you have non-zero units, and you don't need non-zero elements of K which are multiplicatively independent, then for some I, ei or minus ei is a primitive root mod p for infinitely many primes in m epsilon. And not just this is not the one which we get. Suppose if I denote that set by p and p of x denote the set of all primes whose norm is less than or equal to x, then I actually have something like this. There exists an increasing unbounded sequence xn such that the p of xn is less than greater than or equal to xn by log square xn. Okay, so using this lemma, and I also have a real bioquadratic field. So certainly I'll have three. I can get it 3 units, right, which are multiplicative independent because it has rank 3. So out of that, I will have 1 unit which is I'll have a infinite set p contained in m epsilon, and 1 unit which is primitive mod p for every p belongs to p, and also I'll have a unbounded sequence xn such that p of xn is greater than or equal to cxn by log square xn. Okay, so using that, now I know that there are only I have a infinite set p, and p satisfies some properties. So, but in class group I have only finitely many classes. So if I distribute this set of all primes in p into the different classes, I want to claim that there exists at least one class such that for which this is going to be greater than or equal to yn by log square yn for some subsequence. I don't so, but if I don't have any such class, then I'll have actually the modulus of pxn is going to be small o of xn by log x square xn. But now question is, if there is one class as far that this happens, but why that class has to be non-trivial ideal class? That follows from the sigma that I've chosen. Sigma was not in any of those Galois groups that I've chosen. That will make sure that the primes actually belongs to non-trivial ideal class. And since I've taken my class number to be prime, any non-trivial class should generate the class group. So now this generates the class group, and I also from the here I have this. I have this as well as I have this A to B generator, and now I use the sequential variant of the growth lemma that I stated by Gun and Josna. I use that to conclude that this has a Euclidean ideal. So now I think I have one. I'll just take quickly 1 more minute and complete. So this is, if I have K to be like this, then Q of this Hilbert class field is actually just adjoining all root Q and root R and root S, adjoining Q to S. So actually this is, you can actually observe that the only primes that can ramify is Q, R, S and 2. Actually we can observe that in the way I've adjoined this, if you take any of the prime, at least one of this, either in this or this or this or this, it is going to be unramified. So we can conclude that it's going to be unramified in L itself. And now in case if I assume this as a class number 2, then the Hilbert class field is equal to this. And one last thing is that this, so whenever I have a K to be this and I have a class number 2, if whenever the Galois group of H of K over K is actually generated by sigma, then there exists a lift of sigma such that this does not belong to this. This is essentially saying that gal of Q zeta F over K it is not contained in the whatever other part of main theorem I wrote, those Galois groups. It does not contain in that. It is, I can just I will have to just use this linear independenceness, and we have whenever K1 K2 is linearly independent, then gal of K1 K2 over K is isomorphic to gal of K1 over K cross gal of K2 over K. Just using that, I can actually lift that. You can refer to my paper and see the proof. So these are my references, and this is a archive one that this talk was based on this paper. So before I finish, let me wish a happy birthday to Professor Michel. Thank you.